Hello everyone. My name is Joch. I'm one of the many people that worked on the COVID-19 tracker project in Slovenian called Sledilnik. So today I'll try to go over some of the kind of genesis of this project. And I'll touch on a particular aspect of it, which is how it was developed, more particularly what kind of technology we used to develop it. Maybe you know the project, maybe you don't. Essentially, what this is all about is it's all about the data. So the project was all about the data. It still is all about the data. I mean, the pandemic hasn't gone away. Maybe we kind of pretend sometimes that it did go away, but it didn't. So the project is still running. But what is kind of the lesson, maybe the most important lesson that the whole team and maybe even the broader audience, maybe even the society learned is how important the data is when it comes to pandemics in particular, and I mean human life in general, I would say. So basically, I'll go over a couple of steps or things that the project did. And as I said, data is at the core of this endeavor. So basically, the whole thing works like this. Data is harvested from different sources. Data is then stored on GitHub, which is one of the choices that we made, and I'll talk a little bit more about that when we get to that part. Data is then made available through an API, and finally it's visualized on the website. I'll show an example how this website looks like. If you haven't seen it yet, you'll get the picture how that goes. So at the beginning, that was I think March of 2020 when kind of we got kind of first glimpse that these things might be serious and that it's not just a minor fluke that will happily sail over. At that time, the data looked like this. Okay, so basically we had a date and we had a number of new cases for the whole country. And okay, so this is probably roughly how it went. So on the first day, we had one case. I forgot where it was, but there was one. And then it kind of grew exponentially, as you might remember. And at that time, me personally, I started to kind of get interested into that, and I was looking for the data myself. Realized that kind of it was really hard to get. If I remember correctly, the thing that like what was striking for me was that the data was mainly published on Twitter, of all places. I was not a Twitter user at that time, so I kind of joined Twitter for good and for bad, so that I could get these numbers every day. And I started to kind of play for my personal amusement, trying to kind of do something to delude me that, or just maybe to forget about the pandemic. Anyway, that's how I got into contact with other people who were obviously way smarter than me, and also, more kind of capable in collecting the data, and that's when I personally joined the Sledilnik project. So this is how the data started at the beginning, and then it gradually grew, like the different sources, different kinds of data, the ways the data was gathered, and so on and so on. And this is how the data flow looks today, or at least it looked at some point, because this is the way the data flow is structured actually changes basically all the time. It changed throughout the pandemic for various reasons. Some of them, I would say, technical, some of them because it was realized that like the society realized that more data means more insight, and so this data was provided. A lot of the reasons for these changes were, I would say, of political nature as well, mostly like some kind of, I would say, rat races inside certain institutions. But this is how the flow looks today, roughly. I mentioned at the beginning we made this decision to store the data on GitHub, and the data is still available on GitHub. This is just like, so this is the, I believe, the data folder of the, so this is the data repository of Sledilnik on GitHub. And this is just kind of the first, I don't know how many, 15 data sources that are available there. There are many more down there, which I won't show now, but you can see kind of the magnitude of how much data is collected. Why I wanted to show this is because I really, really liked this idea of storing data on GitHub. Mainly for the reason that, basically for two reasons. Because the data was changing all the time, the GitHub kind of provides this nice environment where you can also see the history of the data, right? And also kind of it makes it more, I would say, accessible for more people than you would usually do with an API. Never mind, APIs also need like more management. Also, they need more documentation to make them usable. So I think this was one of the good things that the project did at that time, like the decision to do that. And I think I would really recommend it if you are in this kind of data field. I would really highly recommend that you do something like this. One thing that I would add to this is that I would probably opt for including more metadata into the data, so that you really better understand what certain data means. And this was, I would say, a bit of a mistake we did, because at the beginning, as you saw, the data was really simple, and it was totally obvious. Like you open the CSV file, it was totally clear. Okay. So this is the date, this is the number of cases. But as the data grew, it was really more and more not clear what certain fields meant, right? Now, if you go now into one of these files, yeah, there is a chance that you won't really necessarily understand what's happening. So kind of additional metadata, I would say, would be a good thing to have here. Okay, so if we go to the next stage, so this is the final stage. This is the result of all this data gathering and processing, because there is a lot of it. This is how the website looks like. This is probably 1/3 of the page. It goes like on and on. So I think at the moment we have around 30 visualizations that cover, I would say, quite a lot of aspects of the pandemic data. And this is how the website looks like if we zoom in a little bit. There's a little bit of delay, I'm sorry, between the screen I see and what you see on the page. So essentially you have like an overview, in numbers, and then the visualizations begin. We were kind of going back and forth because this thing grew really kind of organically. We were really considering, like, should we split this in many different pages or not? So a lot of kind of back and forth, and then we, in the end, decided, okay, this is like how it started, and this is how it should be. And I think it's relatively useful way of doing things. Okay, so now for the part that probably you'll find more interesting, I hope, the code. There is a number of different technologies used in the project. So first, and this is really important part, is the code for data pipelines. So all the code that gathers or fetches the data from different sources, validates it, which is also quite important part, so that we know that the data is at least in correct form before we ingest it into the system. Most of this data is written in Python. There are some people in the room who actually are responsible for that, and I'm really grateful for their work because it's a pain in the ass kind of work. A lot of kind of little details that you have to be prepared or kind of react on changes to the data and so on. So this is mostly Python. Since the National Institute of Health launched their own Power BI portal, I think we are also using JavaScript now to scrape some of the data from their portal, but I'm not entirely sure. So, and then we go to the kind of the website, which I want to talk about a little bit more in this talk. And for this, somebody, I know who he is, but somebody just decided that we'll use Vue as a framework for building this thing, right? And because I asked him later, like, what was your motivation to do that? I didn't know the framework that even existed. And he said, no, I didn't know either, but it kind of looked something I wanted to try, right? So he just said, okay, let's use Vue, and this was then used. Okay, so now kind of I have to apologize. I'm not really a JavaScript developer. I mean, I did my share of JavaScript in my life from, I would say, since it was put into the world, for better or for worse. But I'm certainly not an expert, right? So please be gentle when it comes to that part. Okay, so this guy, he chose Vue, and kind of in a similar fashion, although I knew what I was doing, I chose F# and Fable, which maybe you know, maybe you don't. And this is actually the part that I'll go into in more detail, really. So this is kind of the core of my talk. There is also HighCharts. This is a very, very good visualization library. It's a mostly graphing library. I think quite well designed. One of the things that I really like about it is that it's declarative in nature. So basically, you write the configuration of what you want, you provide the data, and then it would render nicely whatever you told it to. Again, I mean, I think it's quite a good tool to use. Again, somebody else brought this to the project, said, look, this is kind of what's good. He's using it at work as well, and I'm really happy that he did so, because otherwise we would have much more work with what we were doing. Okay, so what is this thing called F#? Okay, I'll just read the definition because it's easier. So it's a functional first universal programming language for writing succinct, robust, and performant code. Okay, so it's a mouthful of whatever, but it does mean things, actually. So maybe you are more familiar with C#. So C# is a .NET language. .NET is a kind of development framework from Microsoft. And F# is essentially also from Microsoft, basically targeting the .NET platform, but it has a completely different philosophy and design from C#. It is functional first programming language, which means that it has basically a certain style, like when you use a certain style of programming which more kind of resembles how you think in, like when you're doing math, than like what you might be used when you are writing code in more imperative programming languages like JavaScript or Java or C#, and so on. It is part of the broader family of ML languages. ML, I think, stands for meta language, but not entirely sure. Another kind of good representative from this family is OCaml, which is also a very nice language. Similar to F#, but then there are differences. What is also interesting is that F# is kind of the way it is treated by Microsoft is like kind of, this bastard child. They don't know really like whether they should support it or not. And kind of there's always like this drama around it. But what is actually happening in reality is that a lot of concepts and ideas that the C# is using is actually coming from F#. So you can treat it as understand it also as a kind of this experimental platform that they use to kind of build or develop their flagship language. One thing that people may not know is that this is all open source. Microsoft made a huge effort of open sourcing a lot of their code. The way they're handling the community is kind of so-so. Not everybody is too happy about it, but in principle, this is all open source. You get access to all the code, no problem here. And they made a really great effort to port this, to port the .NET framework so that it works basically on all the major platforms, Unix, macOS, and Windows, which was like historically their primary target. And I mentioned there is, the project basically uses F# / Fable. So what is Fable? Fable is a relatively new project. I think it's basically around 4 years old, something like that. And what it does, it compiles F# code into JavaScript. Basically, you write code in F#, then compile it, or some people would say transpile it. I don't really know what, I mean, kind of have an idea what the difference is, but I'm not entirely sure. So basically, you can say it's a transpiler from F# to JavaScript. So in this way, you get all the benefits of writing kind of functional, nice, beautiful code, and then translate it into JavaScript. As of version 4, which is going to be released soon, Fable will also compile into Python, Rust, Dart, PHP, I think it's experimental, and TypeScript. So kind of there is a lot of things happening at the moment. And I think these are all kind of interesting areas of work. Because it opens a lot of different opportunities. Basically, what is also good to understand is that when you kind of take this approach, you are not, and this is something that people are often afraid of, it's not like take it or leave it approach. Like you don't have to do all your project in F# and forget the JavaScript, right? You can just take like one little part of your code base and do it in JavaScript, do it in F#, which then gets compiled to JavaScript, and then from there on you can use it as like any other JavaScript you write, or TypeScript for that matter, right? So it's kind of, there are various degrees how far you want to go with this. And I think Sledilnik is kind of a good example of that, right? Because it, as you saw, like, so the Chrome, like kind of the website, it's Vue, and then there is a little bit of JavaScript here and there, and then there are these visualizations which form the core, but everything kind of works nicely together, and kind of no major casualties happen during that. I want to talk about a little bit now about the properties of functional style of programming. I don't want to sound this as an kind of like advertising anything, or yeah, I just want to share like what I think is an interesting approach. So what is a functional style of programming? It has a number of components, of which I'll probably list like a couple of those that I think are more important. So the first thing is that functions are treated as a first-class citizens. This used to be, so first, what does that mean? It means that functions play the same role in your programming language as would any other data structures, right? It means that you can assign them to variables, you can pass them to functions, and you can return them from functions. Okay, so you have functions that can accept functions, and these functions can then return functions. This used to be kind of more advanced. I mean, these days it's not so much anymore. I mean, JavaScript totally passes for this definition, right? Because you can basically assign a function to a variable, you can pass it to another function, call it there, you can always return a function. So no kind of big deal here. Although I would say like 15 or 20 years ago, this was kind of not so common, right? Things were not like they are today. But I mean, a very important property nevertheless, right? Then there are varying degrees to this, like whether your language has the concept of a lambda function. I think in JavaScript, this is called an arrow function, correct? Yeah. Which kind of simplifies working in a functional style. So for all practical purposes, we could call JavaScript a functional language as well. The second important part, and this is maybe not so common yet, is that functions are deterministic, right? So you probably remember from high school, maybe even primary school. I don't know when we take functions in Slovenia. Is it primary school maybe? Yeah, okay. So, you go to, I don't know, 8th or 9th grade, and they show you what the function is. And one property that is kind of always understood to be true of a function is that when you call it, it will always yield the same result. Like there is no way, like you call a sign of something, and then you get 2, or I don't know, well, 0.5, and then the next time you call it, you get 0.2, right? It just doesn't happen in mathematics, right? And for a good reason, right? Because that is actually a nice property that you want to have in your programming language. So why in programming languages this is not always the case is because very often we have data that's being mutated. So you assign something to the variable, and then you mutate whatever this variable holds. And this basically then leads to this fact that it can quite often happen that when you call a function, you get the result A, you call it again, you get the result B. And this is like when you try to debug a system like that, it's really hard to do, right? It's because you really have to be clever and understand quite well what's going on behind the scenes, actually, so that you know what kind of monstrosity you produced in your code. I have to say, in F# you have this kind of option to mutate things. So there is an option, and there is sometimes a good reason why you want to do it like that, mostly for performance reasons, but I would say in 99% of cases you don't have to. And again, I think this is a good thing. And now the third part, again, I kind of already mentioned it a little bit, but now I mention it again. The fact that the data is immutable. So you take something, and then it stays fixed for the duration of your scope. When it goes out of scope, it goes out of scope, but it doesn't change, right? You don't kind of poke into your, objects or dictionaries or whatever you want to call them. Like once you create something, it stays the same. And whatever you want to do with it, you always create a new version of it, right? So basically, if you want to do some operation on your dictionary, you take it, and then you create a new version of it. And this used to be, I would say 20, 30 years ago, this used to be a problem because of performance, because you can imagine this kind of code might use more memory, might not be so performant, but in this time, relatively short time, this is not a problem anymore. Also, the compilers got way more clever, and this is now something that's not an issue anymore. And again, you see kind of hints of this even in JavaScript, right? Because now you have this, I think it's const construct, right? Which is exactly that. Like you create something with a const, and that means you know this is not gonna change. Like even if you try to, you can't, right? Which didn't used to be the case, at least when I first looked at JavaScript. Okay, so now I want to go and just give you a little bit of taste of how this kind of programming looks like. It's not gonna be like, probably, these are relatively simple examples, but I hope they will demonstrate a little bit what I'm trying to convey here. So I apologize to the camera because I need to read the screen now so that I know what is happening. So basically, I'll just showcase a number of really small programs that basically try to demonstrate what I was talking in kind of abstract, now in concrete. Okay, so basically what we'll do here is we'll create a list of names, and then we'll do something with it. So first, we have this definition, let names, and we have 3 names. As I mentioned, like let, basically in this case, defines names as immutable. The next thing we do is we define a function which takes one argument, in this case a name, and does something to it, which in this case prepends hello, and comma. You can see from these two definitions that they kind of look the same, right? So there is no kind of distinction, right, between defining a list and defining a function. The only difference is that the second definition kind of has this one parameter, right, which is a name. Okay, and then in the next step, we take this list of names and we pipe it to a map function. I'm sure like most of you are familiar with map function in JavaScript. So another kind of hint where things might be moving. And then the result of this is then passed into iter, which basically is just iterates through the list and then prints whatever the result is, right? So the interesting part in these 4 lines is that you see how in functional style of programming, it's quite easy to create a flow of data, right? With these pipeline operators. Something similar if you are familiar with Unix, shell, it's kind of similar, I mean, more kind of strict and well-defined, but still, you see we have our data and then we pass it through map function, which takes 2 arguments actually. One is the function that does something with the argument, and then the second one is implicitly passed in, and then finally we print this thing to the screen, and you can see what the result would be. So the takeaway here is functions are first-class citizens. They are defined quite similarly to what all the other definitions are. Everything is immutable, and you can create these nice pipelines through which the data flows. Okay, so the next one is kind of similar, except it's maybe a bit more numeric. So first we define the square function, which takes an argument and returns a square of it. In the next step, we define another function, which takes an n, creates a list of integers from 1 to n, and then passes this to map function again, which basically applies a square function to each of the elements of the first list, which again results in another list, which is then passed to the list sum, which takes all the numbers and sums them up to get to the result when we call it in this particular case. One thing that it's not really shown here is that all of this is very strictly typed, which means that if we were to pass as an initial argument where you see 1 to n, if we were to pass a list of arrays here, the compiler would tell us, sorry, but this is not compatible with first the square function, because it would know from the definition of the square function that you cannot multiply strings. And especially the second one, sum, which doesn't take strings as an input. It takes only a list of integers or floats, but not the strings, right? So the compiler would tell us in advance that this is totally the total no-no, and you must be doing something wrong. And this is a very important kind of feature of the language to have. The second kind of important property of functional programming languages is algebraic data types. I have to be kind of more like, I have to say algebraic data types are not kind of tied together with functional programming languages. They are not a must, right? But they usually come with functional programming languages. Although there are cases, like examples of programming languages that are functional in nature, but don't have algebraic data types. For example, Lisp is, or Scheme is such an example. Clojure, maybe. So these are all kind of similar languages, not like weakly typed. They don't really kind of do a lot with types. But in other, I would say most functional programming languages, algebraic types play a very important role. And you might wonder, like, what the hell are algebraic data types? And the good news is that you know half of the answer already. So because you use them, like half of them you use every day, right? These are product types. That's their name, and includes tuples, records. In Python, this would be called dictionaries, namely records. And this is how you define them in F#. You say type, and then your name of the type, and then basically you say what are the fields. In this particular case, we have a name field, and we have an age field, right? Both of which kind of have their own types. One is the string, and one is the integer. Why are these called product types? Maybe not so kind of clear from the beginning, but what you can imagine is that they represent a product of all the possible values of name and age, okay? So they cover like a really big space, right, of all the ages of John and all of ages of Nick and Jim and Jill. And basically they kind of form this product of values. I probably didn't explain this too well, but this is the best I can do, I'm sorry. But I mean, you are very familiar with this because this is like really something you use every day. It's your bread and butter, like you cannot do without this, right? Whether this is masked up as objects of some sorts, as in JavaScript or whatever, I mean, this is kind of very, very common. And then we have the second one, which is a sum type. Functional programming languages are kind of conceptually coming from math. They have much stronger, I would say, theoretical foundations like compared to other languages, right? Which are more often than not like ad hoc hodgepodge of ideas that people find useful, right? But functional programming languages are usually made by mathematicians based on some sort of a mathematical theory that they have, right? And I mean, you may or may not hate math. I mean, developers usually don't. But I would say it's a good thing, right? And it shows, like when you look at the results, it usually shows that it's good to have a solid theoretical foundation when you do something. And algebraic data types come from a field of type theory, whereas like the part that we looked before comes from lambda calculus. These are relatively old concepts already, probably some of them nearly 100 years old. Before we even had computers, these things were like mathematicians were already thinking about them. And I can tell you that they are thinking a lot about a lot of concepts that we'll be using in 50 years, or at least some of you will, because I won't. Too old for that. Okay, back to sum types. This is, again, a definition of a sum type, and what this definition defines is a binary tree, right? So basically, you have nodes, and each node has 2 children, and each child can be another node, or it can be a leaf that carries an integer value. Okay, and if you ever kind of had to deal with trees in a language without sum types, you probably remember how awkward and terrible that is. Like how many things can go wrong, and how kind of really not so well suited that like the language was, because basically you had to use a sort of definition from above, which doesn't really fit the definition below, right? But maybe a question here: does this definition make sense to you? Like, is it understandable what it does? Yes, no? Huh? Okay. No and yes. Okay. Huh? Okay. Sorry. Very good point. Okay, so the asterisk basically is a product from above. Only in this case, it's not a record. It's a tuple. Okay, so it's a tuple with 2 values. Okay, is that clear now? Okay, so in basically how we read this, we have a type of tree that has a leaf of integer or node of 3 times 3. Okay, and you see why they are called product types now much better. Okay, I think that's more that I wanted to say about that. And we'll see now how this looks in practice. Okay, so this is a little kind of example that deals with playing cards. And we have a couple of definitions. So the first definition is about face, whether a card is an ace, king, queen, jack, or a number of integer, right? From 2 to, is it 10? I believe it's 10. It's interesting to note here that you cannot really specify that the number is only allowed the range of 2 to 10. But there are languages where you can even do that. Unfortunately, not F#. But anyway, so a face can be one of these 5 options. And then for color, we have a similar situation: spades, hearts, diamonds, and clubs. And then we have a card. So this is now our playing card. And it's a combination of a face and color, okay? And face can take any of the values above, while color can do the same, but only for the colors, okay? This much, I hope it's clear, right? And then this is how you define now actually 2 playing cards. Ace of hearts would be a tuple with 2 elements, ace and hearts. Pretty kind of it's pretty obvious, right? And 10 of spades, similarly, like we use number 10, and the color is hearts. And this is all kind of nice and dandy, but now let's look how we use that. So when we are dealing with sum types, we are usually using something called pattern matching. Basically, what this thing does is you take your value, and then you deconstruct it to basically different options of how it can be constructed, okay? And basically, we match 10 of spades, in this particular case, with, and then we list these different options, right? One is ace hearts, so we kind of deconstruct the tuple, and then we print like what it is. And again, number 10, spades. And the last 2 are essentially just kind of more fancy pattern matches, because they would match any face, right? This underscores means any value. whereas we are interested in hearts. So we just say we have a heart, and the last one is, again, we are not concerned with face, but the color can be diamonds or clubs. Okay, so this is kind of a nice way to deconstruct what your value is, and then you can act on it. It comes really handy for a lot of different cases. And what is now more interesting is that you get like where, sorry. Okay. Yeah, when you write a code like this, you think, okay, now I'm done. Everything is cool, okay? Okay, this has a little bit of mind of its own. But actually, the compiler tells you that you are not done because you forgot to specify some cases in your match. In this particular case, it tells you that any kind of color of spades is not covered in the above. And if you look, you can see that we do catch the number 10 with spades, but other options we did not actually take care of, right? And this might look kind of trivial, or it might even look as a black magic, which is not. Like, how did now the compiler know, right? And like this particular, because it also tells me this is an example that you didn't cover, right? But since this is kind of backed by a nice, well-founded theory, these things can be done. This is one of the most, in my opinion, one of the most important features of functional programming languages that catches or prevents a wide array of really nasty bugs, right? And because we often as developers, like you write code, you have your mental state, like you kind of keep all these things that are going on in your program in your head, and you kind of, through the code, you act on them. And then you often have this idea, yeah, okay, I know what's going on, but then in reality, you don't, right? You just forget a case like this, right? And this is a very, very common case where people make mistakes. And by using a language like this, a whole set of bugs just goes away. Usually this would be like in kind of treated with writing tests and so on, right? You can catch a lot of these mistakes by writing tests, but even in tests you can of course make mistakes. Okay, so I'll skip the next slide. Like, I'll just go quickly through this. Why does this matter? Because I probably, am I over time? Yeah, okay, I'm over time. Why does this matter? Functional stack makes program easier to compose, understand, and reason about. We talked about this. Come on. Okay, solid type system makes modeling and refactoring almost a joyful experience. It's kind of like when you try this for the first time, like you have a code base of, I don't know, 10,000 lines, and you change some of your types, right? And then you just go, then the compiler tells you, okay, here you have a mismatch, fix that. Okay, you go and you fix that. And then it tells you, okay, here is another mismatch, you go and fix that. And basically it's a kind of routine process of going through these error messages. And when you are done, there is a very good chance that the program is doing whatever you want it to do, right? Whereas in languages like Python, especially if you are not using typing in like annotations, this is just a nightmare. And I had a bad luck of working on a number of those in my career, and I just dread, like, every time I even remember kind of this, like, because you have to follow through all the code, basically through all the code base, and see what kind of mess you made by introducing this particular change. And finally, both of these features provide like a better or deeper foundation of understanding what programming is, right? These things may not be so obvious, I mean, from my silly examples, but maybe like you are not even aware of some of the things that actually do happen, right? In tooling that you use, right? So I can think of two examples. One is Redux. I don't know if that is still a thing. Is it still a thing, Redux? People still use it, right? So Redux comes from a small functional programming language called Elm, which basically introduced this idea, right? I would encourage you to check Elm, not to use it in production or anything, but kind of as a little nice language, not a big language, easy language. But this was introduced there, or the guy that invented the language kind of had this nice idea. Another thing that is relatively new is the hooks in React, which probably you use a lot, right, if you use React these days. And the interesting part about that is that they are using like hooks are based on a concept of effect management, which is a relatively new concept, as luck would have it, which was developed, as luck would have it, in Ljubljana. So two guys from Faculty of Mathematics basically had this idea that you could have these thing effect handlers, wrote a little language around that, wrote their papers, like all the theory and everything else. And then people at Facebook saw that and thought, okay, now this is a really nifty idea. We could use that to develop effect handler, like the hooks, right, in React. And you can see more and more of this pattern where like these concepts are moving from, I would say, like maybe some would consider this academic area to mainstream languages. And I think it's a good thing that this is so. Now for a bit of entertainment. I'm a very boring speaker, but we have a very humorous speaker which will demonstrate what happens if basically the language designers don't have a solid kind of foundations on which they build a language. And I apologize for those who already saw that. And this is the cue for the video now is going to be played. So I hope the sound will also work. No? Okay. Is there any chance that we can get sound here? Okay, no. Okay, so it's going to be boring again. I'll try to narrate what's happening. So you have, this is a JavaScript console. So what is an array plus array? It's an empty string. Okay, so what is an array plus an object? Any ideas? It's an object, okay? And because we know that plus is commutative, right? This is going to be the next case. We just turn around the arguments, and it's a 0, right? So what is an object plus object? it's not a number, which technically is correct, right? Okay, and I'll skip the video now because we are running late, or I'm running late, and just move on to this is a promotion plug now. Can you raise hands, like who has seen this this thing? 1, 2, 3, 4, 5. Okay, do you like it? Not sure. Okay, so this is one way. This is just something I want to share. The only relationship it does have to JavaScript is that it basically breaks with this pattern of single-page applications and allows you to basically render the HTML on the server as it was initially intended. So it's not, I would say it's not useful in all of the cases where you might use the single-page app approach, but for many, many different cases, it's really, really useful and takes a lot of work off the table. Makes things much more simpler. Also conceptually, the way this was designed basically builds on the initial idea of hypermedia. So I would really encourage you to check it out, and basically maybe it will allow you to write less JavaScript code. With that, I thank you very much for your patience, and I'm sorry because I went over time.
We have the sound? Nice. Yeah, thanks again. This is really interesting. Also like going into functional programming and you talking about how Sledilny came to life. And I have a question that's basically, I read somewhere that Fable renders React, or like the output of F# is then React. And since that's a burning question in JavaScript community, like which framework to choose, do you maybe know why they chose React?
So it's a bit of a historic question. So something for you, basically, to investigate now. So historically, the first implementation of Fable was targeting React as a kind of the way virtual DOM and React, how you went about rendering your HTML. These things changed, and now you have a host of options. I think Solid.js, if I remember the name correctly, is now supported. Lit, Svelte. I know of these 4 at least, but React is still kind of maybe the first choice. But you have other choices as well. But then again, I mean, you are not really kind of bound to that. It's just one library which is part of the ecosystem. I mean, you can just render SVGs if you like, or you can just, I don't know, draw to this thing canvas. I mean, it's really up to you, right?
Nice, thanks. Maybe we can have 1 or 2 more questions, and then if you want, you can also find you after. Anyone? Okay.
Good, thank you.
No one? Yeah, okay, let's grab a beer, get some snacks.
Good idea.
And mingle. Thank you so much for coming.
Thank you.